Hello, I have a good news. We have done the difficult concept. We have learned a difficult one, and this is easier. So instead of using the previous methods, you could use first this one and then somehow manage to go on to the other one. So what I mean here is that we learned that how to find the joint CDF of two functions of two random variables, and this was hard. And then it was harder to find the distribution of one function of two random variables. This is a bit easier, and this last one is easiest one. So you may start to solve this one, and using this solution, find this one or find this one. Okay, so let's see how easy is to find a joint DC density or joint PDF of two functions of two random variables, and you see that it's lots of less calculation, less complexity, and so on. So it's very straightforward, and this is why it's always better to or if you can, obviously, start here. There are exceptional cases that is easier to start here and there. And then once you find the solution, go and find these ones and using the methods of marginal distribution. So now what I'm interested is that I have a system with two inputs and two outputs. So this is X, Y, and the outputs are Z and W. And I have, let's say, the joint density of Fxy of X and Y. And I want to know how can I find the joint density of Z and W of Z and W. So how to find these systematically. The good thing about this last part of this chapter is that we present a very systematic approach, a step by step, which is very straightforward. So we have two functions of two random variables and the distribution of that. So there is a theorem here, very easy theorem. We will prove it. And this theorem says that first, for any arbitrary values of Z and W, consider these two equations. This is the first equation, and this was, so remember that you fix these numbers and then you solve these two equations. So you have two systems with two equations, and then you solve it. And then once you solve it, you will obtain a set of solutions. This set of solutions we denote it by A of Z and W. So A of Z and W may be empty. So if you don't have any solution, this set is empty. Or you may have one solution, which is, let's say, X1 and Y1. Or you may have X2 and Y2, two solutions. Or you may have infinite number of solutions. So whatever number of solutions you have, once you get the set of solutions, then the joint PDF of Z and W is obtained by this equation, which is summation over all possible solutions of these two equations, because this guy is the set of all possible solutions of the joint PDF at the solution divided by the Jacobian. The Jacobian at the solution. So the Jacobian is calculated using this one. So remember that this Z, so you remember that you have Z is equal to G of X and Y. So you can calculate derivative of that, derivative of Z with respect to X is just partial derivative of G with respect to X, or the same thing. So because you have two functions, two random, two variables, you have four partial derivatives here. Okay, so you have these ones. So you calculate, and then you calculate the determinant. Remember that this determinant is equal to this guy. The Jacobian is equal to these elements multiplied by this element minus this one like this. So you're going to get partial derivative of Z with partial derivative of X, and then partial derivative of W with partial derivative of Y, minus partial derivative of Z, partial derivative of Y, times partial derivative of W partial derivative of X. Basically, Jacobian is the ratio of the two areas is equal to the ratio of the differential areas. So we have seen in one of the previous videos. So the Jacobian of the transformation. So what we need in order to find the joint PDF of the output is to find the set of solutions and then calculate the solution, the Jacobian at all solutions, and then plug it in these equations. So in 3 steps. So we can move on and then prove this theorem.